Okay, so hope it is recording properly. Yeah, so welcome to class 24, and the topics of discussion will continue to be the foundation uh, levels of statistical mechanics, how statistical mechanics developed, and why we use statistical mechanics. How did the formalism come about? What was the origin of the formalism of StatMech, which basically gave a found foundation, a sound foundation to the assumptions of StatMech in the microcanonical ensemble, in the sense of postulate of equal a priori probability and yes, so all those things. So till now we have been discussing about equilibrium statistical physics, but we have not discussed that a system will indeed reach equilibrium um, if left to itself. Okay, so so what is equilibrium? Equilibrium, as we discussed, is there should not be any transport of any quantity like energy, momentum, density, mass from one region to the other. So basically, all over it should be homogeneous. So and it should not change as a function of time. But even if a system doesn't change as a function of time, you could have currents, energy density current, momentum current flowing through the system, and then the system is not in equilibrium. Then it could be in steady state if the current is time independent. But if is a transport of some quantity from one part of the system to the other, then they won't. Then the system is not in equilibrium. And the point is to show or establish that if there are initial inhomogeneities or non-equilibrium conditions where certain quantities are different in different parts of the system, then there is a method that it will homogenize itself. There will be transport of quantities, relevant quantities from one point to the other, and thereby the system will reach equilibrium if left to itself. But if it is not left to itself, if there's some external driving, then there will continue transport of some quantity per unit area, per unit time, flux, if you like, of some measurable quantity. And how and what is the value of this transport coefficient, the rate of transport per unit area, per unit time, is what is called transport coefficient. And before statistical mechanics, Boltzmann S equal to kb log omega was developed even. Boltzmann worked on the so-called the Boltzmann Transport Equation for dilute gases, says that through collisions, a gas of molecules will reach equilibrium. And what is the method of reaching equilibrium? So this class and the next will be discussion about such issues. And rather than give a long preamble, I think it's better to get into the thing so that you get to know what it is all about. But even before we start discussing about the distribution function, which will come in a moment, I think it is better for you to have an idea of some numbers, which because we will use these numbers to define certain small volumes, to define certain quantities. and there it will make more sense. So some numbers for the gas at STP standard temperature and pressure. It has been covered by this whatever this block is. So some numbers to keep in mind is the average speed of gas molecules at STP standard pressure and room temperature of 25 degrees centigrade or 300 Kelvin, as you might take it, is around 500 meters per second. Of course, the gas molecules have a distribution. All of them are not moving with the same speed. Some are moving very slow, some are moving very fast, and you have the Maxwell-Boltzmann speed distribution. And on the other hand, if you'll talk about just about one component of the velocity, then that's Gaussian, as we have discussed before, right? But an average, a mean velocity, a ballpark number is around 500 meters per second. And just to give you an idea of what this 500 meters per second means, of course, it's very fast, but how fast? So 10 meters per second is 36 kilometers per hour. So 100 meters per second is essentially 360 kilometers per hour. And this is 5 times that. So 360 kilometers per hour into um, 5, so that's I think around 1800 approximately kilometers per hour. So that's the speed of the gas molecules around you in your room. The other point to keep in mind is the value of the mean free path. The value of the mean free path is uh, around 30 nanometer, right? I think 30 nanometer, yeah, 1 nanometer. So maybe should be 10 to minus 8. I'm not sure, but it's around 13 nanometers, 300 times the size of an atom. Just check this number. Is it 30 nanometer or I think it's 30 nanometers, 300 times the size of an atom. And this is the distance that a gas molecule will move on an average before it undergoes a collision. Note that this is larger than the mean average distance between gas molecules. And I mean, so the number density, um, yeah, the number density is of gas molecules is 2.4 into 10 to the power 19 molecules per centimeter cube, and you can convert that into 2.4 into 10 to the power 7 molecules per micron cube. So this is equivalent centimeter. I've just converted it to micron cube. And if you have an idea of these numbers, then you can have an estimate of the mean free path, which is 1 upon root 2 n. N is the number density of gas molecules, and this is the so-called scattering cross section, or broadly, if a molecule is moving in a certain direction, right, and there's a lot of vacant space, just so I mean, if this is the average distance between gas molecules, of course they are moving, so I'm talking about an average distance. Then even as they move, they can pass each other and move to much larger distances before they undergo a certain collision. And the probability of collision will depend upon the solid angle that is subtended by another gas molecule, the cross-sectional area, as this thing is moving in a random direction in all possible directions. So the total amount of solid angle subtended by a much larger sphere will give the probability. So all these things can be calculated in kinetic theory of gases, and I think this is there also in Rife in some chapter 12. But you can look up any kinetic theory of gases books, which like I think there's a basic book. Yeah, just check it up. Uh, and that's where you get these prefactors of root 2 and so on and so forth, and an exact expression for the scattering cross section, which is will be like 4 pi r square, r being the radius upon will it be 4 pi r square, pi r square maybe, where r is the radius of the molecule and so on and so forth, right? So this is the distance. Moreover, the collision time Collision time is so to move this distance of mean free path, and if it had a velocity of 500 meters per second, uh, how much time will it take from one collision to the next? And that is approximately 6 into 10 to the power minus 10 seconds, right? So a molecule collides every tau seconds, and in that case, you can convert it. Uh, yeah, sigma zero I have written here as pi d square. I mean, this again comes from kinetic theory of gases. So d is the diameter, molecular diameter. Yeah, so that's what it and a detailed discussion will be there in the kinetic theory of gases. But talking back about collision time, so a molecule essentially collides around 6 into 10 to the power 9 times in 1 second. Okay. So these numbers will come useful soon. So just to have an idea, so basically, the time elapsed between two collisions is the order of this, and the mean free path is approximately 300 times the size of an atom, 30 nanometers, and so on and so forth. And this is the density, right? And what is the aim of the class? The aim of this discussion, today's class and the next, is to have a microscopic, to calculate transport coefficients from microscopic quantities. So, what is, so again, this is a huge disturbance. I don't know what to do. So, transport coefficient will give you at what rate a certain quantity, like momentum, mass, energy, is being transported across a certain area. So, flux, right? Uh, amount of quantity, a certain quantity is being transported per unit time, per unit area, when a certain gradient is maintained. Gradient of what? So if you maintain a gradient of temperature between 2 points in space, uh, that means that the energy density will be different, and so there will be heat flux from one point to the other, right? And then this thermal conductivity will be the transport coefficient. This is the amount of heat energy which is transported per unit area, per unit time, and that is proportional to the flux, and that's called Fourier's law. And the proportionality constant is kappa, the thermal conductivity, and that's the transport coefficient. And the reason you have this minus sign is that the energy flow is in the opposite direction to the gradient. So whatever is the direction of the dt dx, the heat will flow from a region of higher temperature to the lower temperature. And similarly, if you had different densities of gas molecules, here at certain point it was more dense, and here it was less dense, then you can write down the diffusion constant. So basically mass will be transported by diffusion from this point to the other. And then you can talk about the flux, and this is a vector quantity. Flux is a vector quantity, which is the mass, amount of mass transport per unit area per unit time, and that is proportional to the concentration gradient. And it's proportional. And what is the proportionality constant? That's the macroscopic diffusion constant. Why did I add the word macroscopic? Because this, I mean, initially when it was written down as Fick's law, this was an experimental observation, right? And this was some proportionality constant. You would do some experiment and get out the diffusion constant for different gases, say, or yeah. But the question is, can we calculate these transport coefficients like D, like conductivity, from microscopic considerations, right? So when you have a diffusion, when you have a current, that's a macroscopic quantity, and concentration gradient. Can you also, first two questions. So basically, whether you can calculate D from microscopic considerations, and later, as it will come in 1 or 2 weeks, can you calculate what is the microscopic definition of D? What does it mean microscopically? Macroscopically, yes, there's a net mass transfer, but once you have a microscopic picture, can we talk in more detail about it? So we're going to, so that's what the transport coefficient is. And similarly, kinematic viscosity is something like the diffusion constant for momentum diffusion. Okay, it's not here. So when you write down the Navier-Stokes equation, you can show that this is essentially the diffusion constant for momentum diffusion um, in a fluid. But here, what I have written is the force per unit area. That's the stress, if you like. I mean, force per unit area is stress, and so here you have layers of the fluid, and different layers of the fluid are moving. So suppose the fluid flow is in the x direction, and there is a velocity gradient in the y direction, which means at different values of x, sorry, at different values of y, you have different velocities of fluid. So the top layer is suppose moving fast, this part is moving slow, and even the lower part is moving even slower. So you have a velocity gradient. And if there's a velocity gradient, the top part of the fluid, which is moving faster, will try to pull the fluid. So it will try to give a force and try to pull the fluid faster. So there will be some net force acting on different layers of the fluid. So the force acting between different layers of the fluid moving at different speeds is proportional to, so that's momentum transport force. So force is being applied. So there's some momentum transport if there's a force being applied. And that force is proportional to the velocity gradient. And in that case, eta will be the transport coefficient. And the broad question is, can we calculate these transport coefficients from microscopic considerations? So basically, to calculate such quantities from microscopic considerations, we have to have a discussion of how microscopic transport of energy, momentum, mass is taking place. Uh, and the question is, if there's an inhomogeneous system, what decides or how the system will become homogeneous uh, due to redistribution of whatever quantity was inhomogeneous and reach the situation of equilibrium if left to itself. Uh, the reason we assume that the system will become homogeneous is because the non-homogeneity is being smoothed out by transport of quantities which were from one region to the other, and the transport will keep on happening till there's a temperature gradient, or till the temperature gradient is lost, so that there's uniform temperature all over, or the concentration gradient is lost, and so on and so forth. If left to itself, of course, if you drive it, the current such gradients will remain. So it will not reach equilibrium ever because there's an external driving. So these are the quantities that we are going to discuss. That what are the microscopic mechanisms of transport, and with the same, let's start defining some quantities. And the quantity that we shall define is the so-called molecular distribution function. And in terms of this distribution function, we shall write down or try to calculate various transport properties. But what is the distribution function? So distribution function is denoted by F, at least in Rife. So this distribution function is defined at different points in R. There should be R vector here and a velocity vector here. So at different points in space, you have a distribution function defined. So at each point in space for a particular value of R, you would have gas molecules moving. So within this certain small volume at position R, so suppose this is your axis, and there's a R vector, and in that R vector there's a small volume which has a large number of gas molecules, and these different gas molecules are moving in different directions. Right? Some are moving here like this, and all possible directions, as you would know, because they're colliding with each other and they're moving in all possible directions. And what F RVT into D3R, a small volume in space, and just like you can think of the space as a small volume in space, you can also think of a small volume in velocity space, and that corresponds to basically the number of gas molecules moving in the direction of V, but whose velocities lie between V vector and V plus dV vector. So that defines D3V. And this quantity F D3R D3V is the mean number of gas molecules whose center of mass lies between R and R plus dr, and velocity lies between V and V plus dV, right? So that's what this quantity means. So this is the distribution function. This is the mean density, so if you like. Yeah, so that's how distribution function is defined. And I want to emphasize that at different points in space, FVR need not be uniform. Moreover, at a certain point in space, especially if it's inhomogeneous, and we are going to discuss about inhomogeneous non-equilibrium systems which are trying to relax to equilibrium, and we're discussing about how it is going to relax to equilibrium. So it is possible that in a certain point in space, right here, there might be more gas molecules moving to the right compared to that to the left. So then the value of F for a particular direction, suppose to the right in the plus X direction, will be higher than the F, the value of F for a velocity which is moving in the minus X direction. So you are specifying a point in space, mentioning the volume of space. Now, if you don't have D3R, then it means unit volume in whatever units, right? We'll talk about D3R soon. So then per unit volume, how many particles are moving? So then you would have, if you don't have D3R, then FRVT into D3V will mean how many particles per unit volume are moving in the direction of V vector and V plus dV. That's what it would mean. Moreover, suppose you had a unit volume here, right? So this is somewhere, and there are different number of gas molecules moving in all possible different directions. Some are moving in this direction, some are moving in the plus y direction, some are moving in the minus z direction, and so on and so forth. And some are moving in directions in between these x and y, and so on and so forth. Now, if you summed up the total number of molecules moving in all possible directions, which means you are integrating FRVT over all possible different directions, velocity vectors. So there's an integration where V is varying over all possible velocity vectors. Then what you get per unit volume is the total number of particles in that unit volume, or it's essentially the density of particles at position R, right? Now, both nRT could be, so nRT could be a position of space. And note that I've also added the word time. Why? Because the density could be changing. As there's a flux of particles from one point to the other, the density could be changing, right? So there could be a flux. And hence, density is changing as a function of R, as a function of T. And similarly, F is also a function of R, V, and T, right? And this quantity then is the mean number of molecules whose center of mass lies between, I have already said this. So this is in 6D space. Okay. Now the thing to discuss is, so I said this, so basically what you are doing is discretizing space. So you have gas molecules, you're taking small volumes and asking how many molecules are moving in different directions is at this point in space and time. Now, you're really, so if this is your entire system, you're locally calculating the FRVT, and in a small volume, you can also ask, how many molecules are there in this D3R. So how small can you take this D3R? So this is small in terms of the entire volume, but it should have large enough, but D3R, the small volume should be large enough to have statistically large number of particles. Okay. So as I wrote down before, that 1 micron cube has around 10 to the power 7 molecules. So you could take this small D3R, this small volume in real space, to be 10 micron cube or 1 micron cube, because even then you would have, if you take a 10 micron cube volume, you would have still 10 to the power 8 molecules, and you could have a large number of molecules moving to the left, to the right, towards the up direction, down direction, and so on and so forth. So you are having a statistically large number of particles. If you have a smaller volume, right, you will have fewer particles. And then when you calculate average quantities in that small volume, uh, so if the number of particles is small, then the next volume, so in the next small D3R volume next to it, it could have a different value. I mean, it is going to have a different value, but what you want is that if NR was uniform, statistically, the density would be the same within statistical fluctuations. How much would be the statistical fluctuations? It will be go as 1 by root n, the number of gas molecules. Now it depends upon how much fluctuations you can tolerate. Right? So we are typically interested is to calculate thermodynamic quantities varying in a systematic, in a continuous way across space, or in a monotonic way is one. So you don't want that you have very high momentum here and very large momentum here, and so on and so forth. Now, typically, if you take your D3R to be large enough, you will have a statistically large enough uh, number of molecules within that small volume. So things will vary in a continuous monotonic manner. On the other hand, if you have very small volumes, order of nanometer cube, right, which will have a very few number of molecules, 2 or 3 or 5 molecules, depending upon density when you convert it. With that, you can't do statistical physics with it. Right? You are really looking at discrete molecules then. So your D3R, the point to emphasize, it should be large enough to have statistically large number of particles, so that statistically you say that yes, here on an average so many particles are moving to the right, and at the next point you have a similar number of particles moving to the right and moving to the left. So things thermodynamically average quantities, thermodynamically average over small volumes. I'm not saying over the entire system, because you're looking at, you want to look at gradients, right? So when you calculate over the statistically large number of particles, you get meaningful averages. If your room is 1 meter cube, you can easily take your small volume to be 1 micron cube or 10 micron cube or even 100 micron cube. That's small enough, but much larger than the mean free path. So these volumes must be much larger than the mean free path, so that within a certain volume, there has been a large number of collisions which has taken place, so that locally the system is trying to come to so-called local equilibrium. And similarly, when you're talking about time, and you're going to look at the time evolution, so basically the time between two, so the discreteness is time is small, but it's large enough compared to the collision times, so that from one unit of time to the next, there has been a significant number of collisions, statistically large number of collisions which has taken place. So when we talk about small volumes and small times, they are still much larger than the collision time of gas, collision time of gas molecules, and much larger than the mean free path. Right, so that's what we are talking about. And yeah, so this is a great disturbance. So, so next thing is, if we have FRVT, then what we can easily, no, that's better. No, not necessarily. Okay. So you can have if you can define an FRVT, the distribution function at a function of space and the velocity, you field, sorry, velocity, space and real space, then over small volumes you can calculate the velocity field at different points in space. And what does that mean? So this u average, so you can calculate the velocity fields, the average velocity of the molecules. Molecules are moving in all different directions, but what you could do is calculate what is the average velocity of all these molecules at a certain point in space, and at a different point in space, and at a different point in space. The way you do it is, you calculate, so how many molecules are moving to the right, what is the velocity of Vx value, and how many more molecules are moving to the right with a higher velocity, and similarly to the left, and similarly in all directions. So that corresponds to V vector. So the mean field, this is basically, you are defining a velocity field at different points in space. These points in space are large enough, much larger than the mean free path. So the way you do it is velocity, value of the velocity, how many particles are moving with this velocity, and integrate over all directions of velocity, right? So this is this integration, and that will give you the total velocity of n molecules. But if you want to calculate the mean velocity of this volume element, you divide by the total number of particles in volume d3v. So this is the particle density, if you like. Right. So the point is that at different points in space, you are defining what is the mean velocity of a large number, statistically large number of gas molecules moving here, moving here, moving here. So at different points, you have different velocity vectors. And this is the so-called hydrodynamic velocity, the velocity field that you talk of the Navier-Stokes equation, which is varying in a systematic way, in a monotonic way. Well, not necessarily monotonic, but in a continuous way over space and time without fluctuations. And without fluctuations, if you're calculating the velocity field, that essentially means that you have averaged over a large number of constituent particles, because each of them are moving in different directions, but you can say that yes, at this point in space, on an average, the fluid is moving in this direction. On an average, the moving fluid is changing direction, and on an average, the velocity field at this point in space is uh, different from this, and so on and so forth. So it will vary in a continuous manner. That's the velocity field of Navier-Stokes equation. Just like you can calculate an mean field, velocity field at different points in space, you can also talk about the kinetic energy density at different points in space. And the way you would calculate it is, okay, at this point in space, how many particles are moving with velocity v in a particular direction. But here you don't really care about velocity v vector, but here you care about v square, half mv square, or the contribution. So if a certain number of particles are moving with a certain value and direction of velocity, how much is it contributing to the kinetic energy? So half mv square into density distribution function into d3v for all possible directions, all the different velocities, how they are contributing to half mv square, right? So that's what you are doing. So v square, and this is also a function of v, and that would give the total kinetic energy in a certain volume of space. And if we are talking about the mean kinetic energy of that region, then you divide by the mean number of particles in that volume. So that will give the kinetic energy density at R1, at R2, and R3. Note this, on the left hand side, you have R and T here. And in general, you can talk about any quantity. So suppose particles are moving around in space, right? I mean, in a certain point in space, they are moving around with different velocity. So any quantity which depends upon those velocity or on the distribution function, you could say that as gas molecules are moving in different directions, how much of that quantity, whether it be momentum or whether it be kinetic energy density, is being carried, or you can also calculate just like this: what is the average value of the relevant quantity of your interest in that point in space and time? It better depend upon, I mean, the basically degrees of freedom, R and V, right? So as long as that chi depends upon R and V, I mean, the quantity of interest has to be dependent on the degree of freedom. So in general, at a certain point in space and time, chi will depend upon the number density, just like this, chi into whatever be that quantity, to f rvt to d3v, integrate over all velocity vectors, and that will be the local value of that quantity chi at different points in space and time. So that's how you understand the use of distribution function. Moreover, what you could do is calculate uh, the so if you can calculate at different points in space and time the mean velocity field at that point, you can also talk about the fluctuation of velocity for individual gas molecules I about the mean field at R and T. So this is the velocity of individual gas molecules. You subtract out the mean field at that point, at that time, the average velocity of a collection of gas molecules is U bar. Note that I'm denoting it by bar, and here there's a vector. And the fluctuations Ui, which is Vi minus U bar, I'm going to denote by this Ui, and to differentiate, I'm always going to put this, whatever this is called, let's call it a tail. Yeah. So this is the fluctuations, this is the mean field without the tail, and this is also a velocity vector, and moreover, it's the mean field. So here I couldn't put a, I mean, if you like U bar, and then I should put a hat on top of it, right? So you can write Vi, the velocity of an individual gas molecules at position R in T equal to, and so basically all that I've done is taken it on the other side. So here you have with the tail, which is the fluctuations plus the mean velocity field. Just to give you an idea, just that we are on the same board. So if you calculated average UI over a certain small volume, then the average UI, average over the entire volume, it would be 0. Why? Because average over Vi, the velocity of individual gas molecules, would give you U bar. U bar minus U bar equal to 0, right? So this is the velocity of a gas molecule or a particle. Now let's talk. So we have defined the distribution function at different points in space and time. Hopefully you have got an idea of what is the distribution function. And if we have distribution function defined at different points in space and time, and that's a function of the microscopic degrees of freedom, R and V, right? Then microscopically, we can define a flux. How much of something, mass, momentum, is moving across unit area, pointing in different directions per unit area per unit time. So what is flux? Is the net amount of chi, some quantity, say mvx, to give it a concrete picture, how much of chi is being transported per unit area dA in unit time. All right. So to calculate that, how do we calculate that microscopically? So the way to do it is, suppose you have a small volume here, d3r, which is much larger than your mean free path. It has a statistically large number of gas molecules. It has a mean velocity u bar rt. This volume, I mean, the gas molecules are moving with an finite velocity, right, which is u bar. But within that small volume, at that instant in time, assume that you are putting imaginary area, you are considering an imaginary area dA, whose normal is suppose in the x direction, right? So individual gas molecules UI, right, they are going to cross this, some of them may cross this unit area. So the distance moved by individual gas molecules with respect to the center of mass of that volume element is ui into dt, right? So this ui is this ui. Yeah? So individual gas molecules, they are moving with respect to the center of mass. The center of mass of that volume element is moving with u bar, right? So you are really asking about how much distance a individual gas molecule has moved within that volume element and with respect to the center of mass, right? Because so that's u I into dt. Moreover, the number density of gas molecules moving with velocity vector v is fv into d3v, right? For a particular velocity vector, that's the number of particles moving per unit volume, fv into d3v, right? And so if that is the number of gas molecules moving with velocity v vector, then the net transport, so how many gas molecules have moved on an average v vector in time dt with respect to the center of mass, with how many of them would have crossed this area if they had velocity v, right? If you have very low velocity, you are not going to cross the area. So the number of gas molecules moved across A, which is in the middle of the volume element, is FV d3v. So suppose they have velocity, if they had velocity v vector, then this is the number of gas molecules moving with velocity v vector into the net transport. So this is the distance moved into dA into dt, because if you have a larger area, then larger number of gas molecules will cross. Now, if v is very high, v is very low, then this quantity will be low, because so we are also having ui dot n, where n points in the direction of A. So it's the normal to A. So many molecules number into the net motion across this area into dA into dt will be the number of particles which have moved across A. And remember, I mean, you are looking at a certain instant in time, but you are looking about the mean velocity of that region. So if you like, at a different instant in time, if you were to calculate this, the dA would have moved with the mean velocity. So you are calculating the motion with respect to the mean velocity of dV. How many have crossed dA, right? So this is so dA is moving. dA itself is moving with local velocity u bar. You are looking about the fluctuations of how many particles have moved and how much flux, say mvx, have they carried. So if so many particles have moved across A in time dA dt, they would have also taken with them a certain amount of quantity called chi, which might be mvx, and that would be the flux of mvx across dA per unit area per unit time. So the molecules can carry chi across dA, right? Which is itself moving with u bar RT. So the small volume itself is moving, but this is the transport across. Now, total flux of chi will be number of particles moving from left to right minus right to left in general, right? I mean, if you are talking of mvx, but in general, I mean, some molecules might also be moving in not in the x direction, but in some 45 degrees to the x direction. But even as they are moving in this direction, they are going to cross the area and carry some mvx across that area, right? And so in general, the flux will be the density of particles in RT into I mean, here you're defining the area into ui. This is with this, the fluctuations about the mean velocity into chi at point R and averaged over all directions, right? But different particles are moving in different directions, yet they are transporting. And this is, what is this? This is this. So basically, you're going to use this at a later point in time. So this is the momentum flux being carried per unit time, per unit area. This is basically the momentum which is crossing this area, right? I mean, number of particles which are hitting in this direction and that direction. And that is what is going to give you pressure. What is pressure? If you're in a static room, the number of particles which are hitting and coming back. But here what you have a moving fluid, right? And what is pressure is not how much the entire fluid as a whole moves and hits you, but the pressure is within about the average velocity field. How many particles are hitting? Suppose your room, suppose your finger was moving with the velocity, and how many particles are hitting it and transferring you momentum. So the way to think about it is, uh, suppose you have a river which is flowing, right, with some speed 10 kilometers per hour, and near the banks you have zero velocity, but in the middle you could have 10 or 20 kilometers per hour, right? But the gas molecules are moving at 1500 kilometers or 1800 kilometers per hour, much higher. So the pressure that you will feel is the consequence in a small volume at any point in space within the fluid. I mean, okay, let's think about gas, because we are really talking about momentum transport due to particles moving from one point to the other. In a liquid, you would also have interactions, and that would also contribute to the momentum flux and so on and so forth, right? Because there will be forces acting between different parts of the liquid. So that will also contribute to the pressure and the force and the stress and so on and so forth. So let's really talk about, suppose you have a gas which is flowing, and within it, the amount of collisions that you face, which is over and above the mean velocity, is going to you're going to feel as the pressure. So it's not that in the middle of the fluid you're going to feel a different pressure compared to the end. I mean, compared to the bank, right? In the bank, you don't have for a river, you have zero velocity. In the middle, you might have high velocity. The pressure is the same. Of course, if you really took a huge board, macroscopic board, and put it, you would feel a thrust, but that's not pressure. That's the total momentum of the fluid which is hitting that board. But the pressure is a local quantity. How much momentum is being transported by collisions at a certain point in space, and that is the thing that we calculated. So this is momentum flux. So momentum per unit time carried per unit time per unit area in that small volume of space. And what is momentum per unit time? That's force per unit area. What is force per unit area? That's something like the stress, pressure, if you like. And we discussed really the gas because we ignored interaction. So the expression for the momentum transport that is coming, that is essentially due to mass transport of gas molecules from one point to the other, right? So that's why for a liquid you would have other terms contributing to the to the pressure or the stress and so on and so forth. So in turn, what we have calculated, so this quantity nRT into um, you know this this quantity, this average over all I particles. If you have the distribution function, then ui dot n, ui, the fluctuation about the average for each gas molecule, integrated over all v, right? That would give you the momentum flux at RT. So I'll continue beyond in the next class. I'll just wait for you to realize this. And this is how you calculate flux. If you know FR, the distribution function at different points in space and time, right? So let me stop share. And shall I stop recording?